In this example, I'm going to do Coletta 9-6, and this is all about a merry-go-round that starts from rest and accelerates uniformly over 20 seconds to a final angular velocity of 6 revolutions per minute. There's a lot of things we'd like to find. Maximum linear speed of a person sitting on the merry-go-round, the person's maximum radial acceleration, the angular acceleration of the merry-go-round, and the person's tangential acceleration. All right, let's take this step by step, starting with A. And the real key in all these angular type of questions is figuring out, going between the names and the variables, right? It's even trickier than in the linear one, figuring out what exactly you've been given. For instance, what is this 6 revolutions per minute, right? What does it mean when it says start from rest, and what is our goal, for instance, for part A? So see if you can do the analysis here. Again, for any analysis, you want to tell yourself the story, draw a picture, and particularly here is important is figuring out what is your goal. Go ahead and get started. All right, here's my analysis so far. Since we know the merry-go-round starts from rest and then speeds up, I did a start and end point and figured that I would write down all the information I know about both. So here's the merry-go-round, and then there's a person sitting on it 5 meters from the center. In the beginning, they're at rest, which means their angular velocity is 0. Their linear velocity would be 0 too, but I'm going to write angular velocity is 0. And remember, angular velocity is omega, and that would be like in radians per second. I also know the radius of the person in case I need that. And at the end, I know the time. Let's say the time was 0 here. I know it's 20 seconds later. And I also know we've sped up. So our angular velocity, again, that's omega, is 6.00 revolutions per minute. All right, and then figuring out the goal is another tricky part, just getting the right variable. So we want the maximum linear speed. So linear speed would be like meters per second, and that would be then we'd want v. So this would be the speed, and this is of the person. So this would be like the person's velocity as they're going in the circle here. So that's our goal. Next step would be to make a plan for how to get v given what we know over here. So go ahead and see if you can make that plan, and then go ahead and try to execute it too. Let's just start with the plan, right? So if we want a linear variable and we have an angular variable, they're always just connected by the radius. So here I can find the velocity by just using v equals omega times r. And since I want the max, I want it at the end time when we're done speeding up, not at the start time when we're not moving and not anywhere in between. So then I just have to use this equation, but the key is omega has to be in radians per second. So first I need to convert omega, then just plug in. All right, see if you can execute that plan. All right, this was pretty straightforward. I just did a regular old conversion step here where I know how many radians are in 1 revolution and I know how many minutes are in a second. This gave me my omega in radians per second, which is what I need to plug in here. And then I just plugged in where the radius of the person here was 5 meters, and I got 3.14 meters per second, which seems like, pretty reasonable speed for a person to be going on a merry-go-round. And just double checking that my units are right. If I wasn't careful, I would have meters times radians per second. But remember, radians is just sort of a placeholder unit that doesn't have any dimensions. So when that happens, I can just get rid of it and see that I have meters per second. Great, we're done with part A. Let's go on to part B. All right, in part B, we're asked to find the person's maximum radial acceleration. We've already done a bunch of analysis, and you'll see that I moved over our converted omega in case we need it here. Go ahead and see if you can do the planning and execution for this step. All right, well, first of all, it's good to figure out what variable radial acceleration is and what it means. So that's our goal, is radial acceleration. That's AR, which in the past we've called the centripetal acceleration. So that radial acceleration is a part of the person's acceleration that points in toward the center of the circle and happens because they're constantly changing direction as they're going in the circle. So that we already know one equation for that, v squared over r. And in chapter 9 of the book, we learned a new equation. Instead of using this, we could also use this, r times omega squared. Since it's max, again, we want to do it all at the end time. And we found v, we already know omega, so we could really, in our execution, use either of these two equations, whichever one you like better. All right, go ahead and finish the execution. All right, I decided to use this equation. I plugged in the radius, the angular velocity squared. When I plugged it in, I got 1.97 meters per second squared. And remember, I can ignore this radian, so I just have meters per second squared for the units. All right, let's move on to part C, where we want to find the angular acceleration of the merry-go-round. So I'll clear up some space here. Go ahead and pause and see how much of the execution and planning, the analysis and planning you can do, and then we'll move on to the execution. Okay, so here in part C, goal is angular acceleration of the merry-go-round. The variable for that is alpha. So our goal is to find angular acceleration. And at this point, it can be kind of helpful to think of the linear analog. Like, what if we were asked to find acceleration? What would we need to know? Well, we could, if we knew it wasn't changing in time, then we could either use our kinematics equations, or we could use the definition of average acceleration. And so similarly, in the angular case, we again have those two options, right? So alpha is constant, so we can either use our angular kinematics, or we could just use this equation right here, the definition of angular acceleration. Now, when alpha is constant, these two are the same. If alpha was changing, then we wouldn't want to use this one, the average one. All right, so I want to do an example where I show you sort of how to do the angular kinematics. So even though it's a little more complicated, I'm going to do the first one. If you did the second one, that's completely fine. But you could try rethinking of it just to practice your angular kinematics. All right, so angular kinematics, then we want to go to our strategy sheet. And we've already done part one, determine if using the kinematics equation is the correct approach, because angular acceleration is constant. It's not changing in time. And we don't have the words average in there. We've already even made our drawings here and had a start and end time. This is the positive direction, right? So we already know that it's spinning positively, so we don't even have to do what we did in linear kinematics, which is set our origin and set our direction that was positive, because this is defined as counterclockwise rotation is positive. I've chosen my start and end times, and I even made this one t equals 0. So now I might want to write down my knowns. I already have my goal, and I want to double check that I'm not missing too many variables. And then I just go through the kinematics from there. So see how much of the kinematics execution you can do. All right, here's all my knowns. I know it's taken 20 seconds. I know I started from rest, and I know my end angular velocity. I could also just set my origin so that I haven't rotated at all, right? So 0 angular displacement and time equals 0. That seems reasonable since I'm not moving. And then I don't know how far I've rotated, which is theta. My goal is alpha. So at this point, you might want to think of this like a linear problem. It'll seem a little less intimidating. Imagine I knew my time, my start velocity, my end velocity, my initial position was 0. I don't know my final position. And what I'd like to know is my acceleration. All right, so now the next step is to go into the kinematics equations and choose one that connects our knowns and goals. Let's do that now. Here's the equation I'm going to use. Go ahead and see if you can actually execute the rest of this problem. Once I figured out which kinematics equation to use, the execution really wasn't that bad, right? I just did some algebra. I ended up with this equation, which actually looks very similar to that equation, which is why either one of them will work. Plugged in my numbers, and I got 0.0314 radians per second squared. I was careful with my units. I had radians up here, seconds, and then I divided once more by seconds to get it squared. Indeed, if this is an angular acceleration, it should be the rate of change of our angular velocity, or radians per second, radians per second squared. Great, so I'm done with part C, and now I need to move on to the last part, part D. All right, so we want the person's tangential acceleration here. I've left a spot for you to fill in the goal in your analysis. That's really the only part of the analysis that left, because we really have all this that we know, and we also even know alpha now, right here. Maybe I'll write it over here so it's over in my analysis. So see if you can do the analysis and planning. All right, so our goal is our tangential acceleration. The symbol for that is AT. And if I think about what that is, here's the person going in the circle. And what happens is, because the merry-go-round's speeding up, they have some acceleration both in the direction that they're going along the circle. That's the tangential acceleration. And then they also have the regular centripetal or radial acceleration pointing inwards. This one we've already found. This is the one we want to find now. And if you remember, tangential, or the linear variables, and the angular variables, so here tangential acceleration and angular acceleration, are easily connected. See if you can think of that connection equation and finish the problem. So the equation that connects them is just this simple one, that the tangential acceleration equals the radius times the angular acceleration. Remember, this has to be in radians per second squared. We already have that here. We know the radius. And so when I just plug it in, I get this here. And if you see, if I'm careful with my units, I get meters per second squared, which is exactly what we expect for an acceleration that is a linear, a tangential, or radial acceleration, I expect meters per second squared, unlike in an angular acceleration where I expect radians per second squared. So great, I finished this problem.